Hello, this is Professor Kuehn. Let's continue our discussion of time dilation. You might remember in my last lecture, we were considering a clock that consists of a ball bouncing back and forth between two bumpers on a spaceship. On the spaceship is riding a man named Luke, and Luke is watching this ball bounce back and forth. You might remember the ball is moving up and down across the spaceship at a speed u. Then there's another astronaut named John who observes Luke, his clock, and his spaceship all rushing past at a speed v. And the question is, what is the time between ticks of this clock as measured by John compared to the time between ticks of this clock as measured by Luke? So I've denoted, notice this picture here, I've shown Luke rushing past. According to Luke, of course, the ball is simply bouncing up and down across his ship. But according to John, he sees the ship rushing past. So I've shown three different instances of the position of this ship as it's rushing past John. At first, on the left-hand side, the ball leaves the bottom bumper. In the middle image, it bounces off the top bumper, and in the third image, it then returns to the bottom bumper. So the time between ticks of the clock is denoted by the time between bounces off of the bottom bumper. So delta TL is the time between ticks of Luke's clock as measured by Luke himself. Delta T sub j is a time between ticks of Luke's clock as measured by John, who sees the clock rushing past. So let's do a little bit of mathematics and find the relationship between these two quantities. You might remember that delta TL was just the distance that the ball moves, which is 2d, that's up and down across the spaceship. The spaceship has a thickness of d, so it's 2d divided by the speed of the ball, which was u. What about the time between ticks as measured by John? Well, that's delta Tj would be 2s over w. Remember, s would be the length of this line segment right here because it's moving along a diagonal, and this would be s also. So 2s would be the distance, and w would be the speed of this ball as measured by John. Well, what is s? S, we can just use the Pythagorean theorem. We can just say that it is the distance that the ball moves horizontally. Let's say this distance right here, we'll call that distance x, and then there's another distance x right here. Okay, so s right here, and then the thickness of the ship is d, so s is going to be equal to x squared plus d squared square root. That's just the Pythagorean theorem. What about w? What is the speed of this ship? What is the speed of this ball as it's rushing past John? Well, you might remember the speed of the ball is u in the vertical direction, and the speed of the ship is v in the horizontal direction. So once again, we can use the Pythagorean theorem to find out the speed of this ball compared to John. Okay, one other thing that's going to be useful, what is this quantity x? Well, x is the distance that the ship moves during half the time of a tick. Okay, so we can write this x as being the velocity of the ship times half the time between ticks, which would be delta t according to John divided by 2. So John measures a time between ticks delta tj, and so half that time multiplied the velocity would be the distance that the ship moves during that time. Okay, so let's go ahead and plug these numbers in. So delta t sub j is going to be written this way, 2s over w. What is 2s? It's 2 times, make a big square root here because there's going to be a lot underneath it, 2 times v delta t j over 2 squared, that's x squared, plus d squared, and divide that by v squared plus u squared, square root. So I've plugged in these various quantities for s and for w. Okay, let's go up here. All right, we can simplify this. Actually, let's square both sides. Delta tj squared, that'll get rid of the square roots, is going to be equal to 4 times v squared delta t j squared over 4 plus d squared divided by v squared plus u squared. We squared both sides. Now let's multiply both sides through by the denominator. So delta t j squared, this is just some algebra here, times v squared plus u squared equals v squared times delta t j squared plus 4d squared. Now let's see, why don't we move this term, let's collect the delta tj's. So delta tj squared times, I have a v squared plus u squared minus v squared equals 4d squared. So I've moved this term over to the other side, of course, to get down to here. Notice that the v squareds cancel, and you get delta t sub j squared times u squared equals, oops, that's a times, u squared equals 4d squared. Or if I move the u to the denominator and take the square root, I'll get delta t j is equal to 2d over u. So the time between ticks of John's clock, notice that's exactly the same as the time between ticks of Luke's clock. That kind of makes sense to us because we're used to the idea that clocks, the rate of ticking does not depend on the speed of this clock. So we've assumed that all of our understanding has been unchanged by the fact that this ship is moving. In particular, we're saying, remember why this happened, because although the ball has to move a larger distance, we can add the speed of the ship to the speed of the ball to get a new speed, w, and those things conspire in such a way to keep the time between ticks the same. Okay? Now, there's nothing really opposed to your common sense here so far. I know we had to do a little bit of algebra, which you kind of have to slog through, but the idea here is that nothing goes against your common sense. But notice that that's only because we could add the speed of the ship to the speed of the ball. In the next experiment, or the next thought experiment we're going to do, we're going to imagine a similar kind of experiment, but instead of a ball bouncing back and forth, we're going to consider a light beam bouncing back and forth. That is, the clock is going to consist of two mirrors and light bouncing up and down across the mirrors. That situation is going to be different. Why? Because light moves at a speed c with respect to any observer, regardless of the motion of the source of light compared to that observer. So we're not going to have a situation where we can add the speed of the ship to the speed of the light. And that's going to give us a very different outcome. So we'll pause there and come back to that next time.